Vic, for organizing this session. So I'd like to look a bit more at this connectivity matrix or correlation matrix. And this talk is going to be with a bit of math, but hopefully not too much. So, from a big picture, the kind of conceptual models we'd like to be manipulating are models that relate different functions together, right? This is a figure I found in a cognitive neuroscience paper a while ago. So this is maybe the kind of things we'd like to be working with. And in practice, a typical functional connectivity analysis that I'll be interested in builds, from a bunch of functional regions. And then what people do is they'll build a set of functional connections, and I'll detail a bit what meaning this can have. And then maybe they'll be interested in variations in these connections, just like what Emily mentioned. So the outline of my talk is, in a first and longer part, I'd like to discuss estimating connectomes. So I call a connectome this representation of connectivity in the brain. And then in a shorter part, I'd like to discuss why it might be interesting to use a different set of objects to compare connectomes. So, about estimating connectomes, and here I'm focused on functional connectomes, right? So as I said, this is the kind of graphs that people are interested in. So the wish list, I guess, would be that ideally we would like causal links. So the idea that the visual information is manipulated in a spatial integration module that then there's information flow that goes from there to a module that controls saccades, and eventually it loops back to behavior. So if we want to put maybe a bit of a generative model on this, we would have a directed model where the signal of one region is given as a function of the signal of other regions. Now, in practice, we're dealing with fMRI, and it's not ideal. We can't trust the delays, so hence the failure of granular causality that Vic has already mentioned. A big hurdle is that we have fairly few samples. We're looking at a few hundred samples per subject, and we often have many signals. So Emily just told us that she liked to work with 200 to 300 regions. And on top of this, we've got really horrible noise that is structured. So my opinion is that causal models in such situations are not viable. So there's something that's intermediate that may or may not be viable, is to capture the independent structure between those regions. So here, the kind of stuff that we'd like to capture is knowing the information in the IPS, then the FEF is independent from V2 and MT. That, I think, is a useful information, and maybe we can capture this. So that's the conceptual picture. In practice, we have correlation matrices, and we'd like to go from these correlation matrices to conditional independent structures. And I'd like to stress that thresholding correlation matrices is not going to work for many reasons. One of them was mentioned by Vic, is basically by chance you'll just have high correlations, but we can also put a bit more math on this. So bear with me. The simplest possible model we can use here is the multivariate model. And I've written the PDF here, but the interesting thing really is that this model, so it's just a Gaussian PDF, by the way, but the important thing is that so X here is the signal. It's parameterized by the inverse of the covariance matrix. So if my signals are normalized, it's the inverse of the correlation matrix. So this inverse of the covariance matrix so it's often called the inverse covariance or the precision matrix. And the important thing is it gives the conditional covariances or the partial correlations between regions. And this is maybe the crucial quantity that might be interesting for the questions that we would like to ask. The other thing this model gives us is a natural goodness of fit, which can be useful to validate models that I'll be using after. So to summarize a bit conceptually, we have observations, there are correlations, there are covariances. The problem is they capture indirect links, right? If region 1 and region 2 are linked, but also region 1 and region 0 are linked, then 2 and 0 correlate. Always. What we would really like to get at is only direct connections, and from a conceptual standpoint, inverse covariance tends to capture this more because it's looking at partial or conditional correlations. Okay? So what we would like to estimate is the independence structure, sometimes known as the Markov graph. And as I mentioned, because the inverse covariance gives us the conditional relationships, if I have zeros in the inverse covariance, if I have zeros in partial correlations, then I get conditional independence, which is something I may be interested in because it's easier to interpret. So it might be a good way of reflecting the large scale brain interaction structure. Now the problem is we don't have a lot of data. So I have an extremely ill-posed problem here with 200 to 300 regions and 100 to 200 time points. I just cannot estimate those partial correlations. I have a multicollinearity problem. That said, if I know that a given region is linked to only 3 regions, then it's only those 3 regions that matter. So my 200 time points are plenty. So I have a chicken and egg problem. If I know the independent structure, I can estimate the partial correlations. If I know the partial correlations, I can conclude on the conditional independence structure. So what works best in practice is to do joint estimation, which is to say that we're going to estimate an inverse covariance by imposing some sparsity, so putting a lot of the inverse covariance to 0. So it's basically solving those 2 problems jointly. To put a bit of math, the way we do these things is that we're going to do something that looks like a maximum likelihood fit of the Gaussian model, but on top of this, we're going to add a term that imposes a sparsity, which is a N1 penalty used in Lasso problems, for instance, in machine learning. So you just fit this. This is a fairly standard model, by the way. It was introduced by Jerome Friedman in 2008. And it's been used a lot in neuroimaging. So you fit this, and you get data that in a cross-validation setting fits much more new data. So you get a graphical model, so a Gaussian model that fits much better left-out data in a cross-validated setting. So your maximum likelihood may look nice, but if you're bringing new data, it doesn't explain it at all. Whereas the sparse model explains it much better. Now there are really strong problems with sparsity. The first one is that theoretically you can show that you need a fair amount of data to recover edges. If I have S edges and P nodes, then I basically need S plus P log P samples. Now quite quickly this becomes not possible in fMRI if I have, say 200 nodes. So basically recovering the independent structure will not work even with sparse models. And then there's another problem, which is that high-degree nodes are much harder to recover, and it's quite easy to understand. They're correlated with many other nodes, hence they're hard to recover. So by construction, those sparse models will tend to decrease the degree of the graph, and that's why the people who like small word analysis do not like them. Empirically, we have found that when you you have a hyperparameter to set that controls how sparse things are. When you set this hyperparameter, you find that the optimal graph is almost dense. And there are many reasons that could explain this. But basically what I'm trying to say is that sparsity is not a magic bullet. So we tried to improve things by, say, adding more data by concatenating more subjects, because we have only limited amount of data per subject. And then what you get is that it doesn't work better because you're hitting intersubject variability. So just, forgetting intersubject variability, concatenating everybody doesn't work better. So then, what we did historically was to say we're going to look for joint independent structure, but different regions, different values. and come up with a nice model to do this, which imposes joint sparsity across edges, and it works better in the sense that it explains left out data better, and it gives you a sparser model. So we were happy, and we thought that we had solved the problem. And if you look at the independent structure, this is a subject sparse structure. This is a population sparse one, so it's much sparser, much easier to interpret, isn't it? Okay, it's a bit hard to interpret, so we can look at things like modularity of this graph, and this is with a non-sparse graph, and this is with a population sparse graph, and here we can see a structure that is much closer to known structure. So we can claim it's a better structure. We're quite convinced it's a better structure. However, so that was 7 years ago. And for 7 years, we've been playing with this. And I've been moving away from sparsity because it's extremely finicky. It's sensitive to the hyperparameter. It's slow and not always doesn't converge extremely reliably. And you could say, okay, that's an algorithmic problem. It can be solved, but it's hard to solve. And most importantly, the set of selected edges is extremely unstable. And it goes back to the fact that we probably don't have enough samples per subject to really guarantee a good sparsity. So what we've been using these days is basically a soft shrinkage, and what's known as an L2 shrinkage. And the nice thing is, so basically you're doing a combination of your correlation matrix and the identity. And there is a nice oracle, which is known as the Low-Dwarf oracle, that allows you to set the hyperparameter directly. So the nice thing is this is extremely reliable, extremely cheap. It may be a bit suboptimal to estimate the independent structure, but I'll show you in the next part that maybe this independent structure is overrated. Okay, and we've been doing like fancier techniques than Low-Dwarf that improve, but anyhow, the big idea is there. So it's a very simple formula, by the way. Don't re-implement it. Download Python or MATLAB code to do it. So I've talked about estimating connectomes, and I've talked about a conditional independent structure. So in terms of interpreting a connectome, this is great. But now what if you want to compare connectomes across subjects? And so Emily did a great talk that introduced this problem very well. The challenge is the following. This is real data, and we have 3 controls and 1 patient with a fairly large lesion. So can you tell me where are the significant differences between those, the patient and the controls? Well, honestly, there's one that's pretty obvious. It's this guy here. But what about the rest? The challenge here, you can see it with your naked eyes, is that everything varies in a very structured way across the different controls. And if we do a bit of math, the problem is that we can't just add and subtract correlation matrices, because if we do this, we're going to create objects that are not definite positive, they're not correlation matrices, they're not covariance matrices. So from a mathematical perspective, that's the challenge. So we can say, let's work on partial correlations, but they're pretty hard to estimate. They're pretty noisy, and it's quite hard to do statistics there. So what we can do is we can do a small simulation to understand things better with a very simple model. So I've simulated 2 different graphs, small ones that vary by one and only one edge in their partial correlations. So they've got one, focal difference in their partial correlation, and the covariances, on the other hand, have an extremely distributed difference, and it's because of the fact that covariances capture indirect effects. So this is not surprising. Now I add a bit of noise, and I sample a family of these, a family of model 1 and family of model 2, and then I look at the estimation error, both on the inverse covariance and on the covariance. And then the problem is, so I've plotted this as colors, the mean square error. The problem is that the mean square error is extremely inhomogeneous. This is very well understood from a theoretical perspective, but from a signal detection theory, we have a huge problem here. We have extremely inhomogeneous noise and sometimes non-local effects. So it means that we could very well be detecting one edge. Say, look this guy. This guy has the smallest error. And if we're doing statistic on the covariance matrix, we might just be detecting a difference here, whereas our actual generative process has a difference here. Okay? Now, I can put a bit of math on this, and I'll walk you through this just to show you that this is principled. We can quantify the geometry of the error on those objects. It's basically, so the thing is, a correlation matrix or covariance matrix is actually an estimate from the data. It's not the data itself. Because it's an estimate, its error geometry is given by the properties of estimators, things that are known like the Cramer-Rao bound when you have enough data, and the asymptotics are given by an object that's known as the Fisher information matrix. Quite surprisingly, this object actually defines a space of models, a manifold. And this is going a bit far, but it has a very nice structure, and you can do a lot of math on this in the specific case of covariance matrices. So people have done math. Historically, it wasn't in functional connectivity. It was in DTI. But people have done math, and we can reuse it to build a mapping from this inhomogeneous error geometry space to a homogeneous error geometry space. So basically, you can do the math to make sure that the estimation error is completely homogeneous. And the formula is actually very simple. You take the control matrix or the group control matrix, and you use it to whiten the time series. And you compute a new correlation matrix like this. This is actually very easy to implement. It's not hard. Now, if we do this on the simulations, we basically get that the math works and that we have perfectly uniform MSE, and that our parameterization, which I call d sigma, is fairly local. So this is a good situation to try to detect variations. And if we do this on the real data, it works. You have extremely uniform estimation error on the controls. On this patient, you can see things that are basically sticking out very well with your naked eye. So this is a very good setting to do detection. And the nice thing is you can map those detected edges back to the brain because you're still in a matrix that is relating RI to RI. Now, we did this in 2010, and we can convince anybody because neuroimages don't care about error geometry and manifolds and things like this. Recently, comparing connectomes has become important with the idea of predictive connectomics. And so recently, we've been building a lot of predictive pipelines where basically, it's a fairly standard pipeline. We extract signal from our eyes, we build time series, we build a functional connectivity matrix, and then we do some supervised learning on this. Very related to what Emily was presenting. So we thought, how about we go back to what we did and try it and see if it works. And so to make a long story short, we've been applying this to a lot of data sets. And quite systematically, this parameterization outperforms and gives better predictive power. So I'm pretty convinced it's important, and that's why I'm, talking about work that's now 7 years old. So to wrap up, I've talked about estimating a functional connectome and about sparsity. The reason we're interested in sparsity is that zeros and inverse covariance give conditional independence, so that might be interesting. But in some cases, you don't need this. And in this case, I would suggest to look at shrinkage. It's just more robust. And typically, the Ledouavov estimator is a very good one. And if you want to compare connectomes, then I suggest you have a look at the tangent space because it's been working beautifully for us. All this, by the way, is available in NiLearn, which is a Python toolbox for machine learning for neuroimaging. Thank you.
Great. Okay, this time we've got some time for questions. You'll have to come up to the microphone. Okay, so while we're waiting for questioners to appear, let me ask a few questions myself. So you've packed in a lot of stuff there,
yeah.
Fantastic graphics. give us a bit of a hint about dimensions. So numbers of nodes you're ending up with, time points, the impacts these things might be having on some of this stuff.
Right. So what we found is that, so if you look at those works, what we found is that we're typically in the 1 to 200 nodes. So we're a bit lower than Emily. If we try to look at the impact of the number of nodes on the predictive power. It's very noisy, by the way. It's extremely noisy. So, you got to look at those graphs and squint. But overall, and the number of time points is just like Emily. So we're in the 1 to 200, typically in the 1 to 200 time points. We haven't looked a lot at HCP because there isn't a lot of variability in the phenotype in HCP. So maybe we should do this.
Okay, now, all right, I guess we haven't got any questions, so let me continue with some more. I guess this was resting state stuff. What about some speculations about task-based kind of data and the extent to which these kinds of approaches could be applicable or perhaps need to be modified?
So in terms of task, I think it's really important to make a difference between whether you're looking at the whole data, so ongoing and evoked activity lumped together, or whether you're trying to focus on the evoked activity. So something that has gotten out of fashion, but that was done a while ago, was to fit like some form of beta series regression, so some form of first level GLM to try to capture only the response to the stimuli and remove the huge variance that is explained by ongoing activity that's kind of below this. I think that if you're looking at the whole thing, so ongoing and evoked activity, things will just carry over. Now, if you're looking at fitting a beta series regression, then you're going to have even less time point, and you're really going to want to use very simple models. And so typically you're going to be looking at a handful, maybe a few handfuls of regions. But the good news is then you should also be able to use your paradigm to reduce the number. To focus on the important parts of the brain.
Okay, just one more quick comment then, because some of you might be getting worried about some of the maths that Gael so happily displayed. He, however, was very judicious in mentioning DTI. So some of the maths he's alluding to, the DTI community is familiar with. One of the underlying messages of our skeptical neuroimaging group is not to suggest that you need to go and learn all the stat that you don't know, but rather to recognise that maybe you need to find somebody who knows the stuff and bring them into your team. And this is probably a situation where that's the kind of thing that applies. Okay, so we thank Gael again.